Okay, so now we finally get to revisit example 10, our warm-up question. And we saw in the warm-up that there were these two ways we could have calculated the flux based on what we learned the last couple of lessons. But now we're going to add a new way you could think about this problem into the mix. If you recall from the warm-up, we found that this was an incompressible field, that the divergence was zero everywhere. And since that's the case, there must be a vector field where we could write F as the curl of that vector field. And you may be saying, wait, why? But I want you to recall earlier that we showed that the divergence of a curl vector field is zero for any vector field G. And so if you have an incompressible field, it's possible to rewrite that as the curl of some other field. And so we're going to go backwards and try to find how we could write F as the curl of some other G. See if you want to put this on pause and see if you can just play around. You're literally just going to play around with the definition of curl to see, is there some vector field when you take its curl, you could end up with this again. So take a moment, put it on pause and see if you can find it. Okay. So here I'm going to do it. I guess I'm using MN and P instead of PQ and R, no problem. And the reason we're doing this is if we can rewrite F as a curl, then we could use Stokes' theorem, because finding the flux of a curl is the same as just integrating over the boundary and finding the circulation. So this is where we're headed. If we can find G, we're going to find the circulation of G around the boundary of our bowl up here. I didn't even draw the bowl again. Let's redraw it. Where this is our boundary. This is where we're headed, but we need to figure out this vector field G. So we're kind of guessing, and what I'm doing is just writing out the general form of the curl of a general vector field G, and then setting these equal to each other, saying I want this to be this, I want this to be zero, and then I want the K components to match. So guessing and checking is going to tell me that P sub Y minus equals P sub X is going to be zero. And the way I'm getting, let's see, where am I getting that for you? The easiest way to see that, yeah, this was not done super scientifically. I was literally just saying, well, I know that I need, really what I looked at is I need Py minus Nz to be negative 3xz squared. And so I have a negative here, so what if I just let Nz be 3x squared? That was kind of my first intuition. And then here, the z cubed, I thought, well, I need n sub x minus m sub y, so I could let z cubed be n sub x. These had to both give me the same, when I integrate them, I had to get the same consistent n. So notice when I integrate this with respect to z, I'm getting back to xz cubed. And when I integrate this with respect to x, I'm also getting back to xz cubed. So in some ways, that was kind of a lucky way to start. But one possible G we could have then is this. We could also have this up to any constants. I could have a constant here plus a constant plus a constant. And you could even have, functions of, yeah, this is basically the easiest one you could come up with. Okay, so now let's take this vector field G that we found and apply Stokes to it. So what we just said is G, when we take its curl, gets us to F. And we would like to know the flux of F. So that's really asking for the flux of the curl of G. And that is equivalent to the circulation thanks to Stokes. So let's just calculate the circulation around the boundary by parameterizing. We are going clockwise so that n will point outwards because that's the direction of the flux vector that we already have established. And then when you do this line integral, you go back to the exact same answer that we had before. So this is a nice connection between divergence or finding flux and using Stokes. That will work sometimes. It really is only going to work if you have an incompressible vector field where the divergence is zero everywhere for your F. All right, that's the end of this section. So we've got one last lesson to go for the semester. I'll see you guys in that lesson.